Hello viewers, welcome to my channel Connect Civilians. So in the second lecture of the eccentric rectangular footing design for biaxial movement, we will go for the design of the reinforcement. So we have already done the up to the depth calculation, depth of the footing. So here we have chosen the total depth as 500, cover will be 50, dia of the first and second will be 12 mm. So effective depth of the bar for first layer will come as 500, that is total depth minus you cover minus dia bar by 2, so it will come as 444 mm, which is greater than our effective depth calculated for x direction, that is 187 mm. So this will be safe. Similarly for y direction, it is 500 minus 50 minus 12, that is the dia of the bar of first layer, minus 12 by 2, that is the center of dia bar of second layer. Okay, so it will come as 432. Okay, so it is greater than 152 mm, so this will also be okay, and you have to also calculate the average depth for the two-way check. Okay, so we have done that also. 444 plus 432 by 2, so it will be 438 mm. Now we will go for the calculation of reinforcement. So first we will go for the calculation of reinforcement, that is parallel to x direction, that is the lower layer bar. Okay, so it will be like this. So formula will be 50 multiply FCK by Fy in bracket 1 minus square root of 1 minus 4.6 MUX. So this will be the moment in x direction by FCK BD square. So 50 multiply by 25 by 500 in bracket 1 minus square root of 1 minus 4.6, and the moment in x direction, that was 233 into 10 to the power 6 divided by FCK, that is 25, into B, that is the width of the footing, that is 2000, into D square, that is the effective depth of the footing in x direction, that is 444 multiplied 444. So your percentage still will come as 0.14%. Now we can calculate the area of bar also from here. 0.14 divided by 100 multiplied by the width of the footing multiplied by the effective depth, so it will come as 1240 mm square, which is greater than, which should be greater than and always be greater than AST minimum, that is 0.12% of gross area for HYAT bars. Okay, so for our minimum will come as 1200 mm square. If you calculate, so it will come as 1200 mm square. Okay, wait. So 1200 mm square. So 1240 is greater than 1200 mm square. How it is calculated, we have already done in our previous lecture for the footing design, so you can check from there. Okay, so it will, so you have to take the greater value, so it is 1240 mm. So number of bar we can calculate from the area of reinforcement calculated, so it will come, and number of bar will be equal to 1240 divided by the area of bar that we have taken for the reinforcement. So we have taken 12 mm dia bar, that will be pi d square by 4, so our number of bar will become as 11 number. So we have taking 13 number of bar here. Okay, why we have taken 13, why we have not taken 11 or 12? So you can easily pass for in spacing also. Okay, I will show you here. So we can calculate center of spacing, so it will be 2000, that is the total width of the footing, minus cover from both the sides, minus center of bars from both the sides, that is 12 by 2 by 12 by 2 divided by number of bar by 1. So number of bar will taken as 13 minus 1. Okay, so it will come as 157 mm. Now we have to calculate the clear spacing. So clear spacing will be 157 minus half of the bar minus half of the bar, so it will come as 145 mm, which is less than 150 mm. Then only this will be okay. If it is greater than 150, so you have to again increase the number of bar. Okay, that's why we have taken more bar. It should not be greater than 150 mm. If you are choosing FE 500, if you choose FE 415, so it should not be greater than 180 mm. This was mentioned in IS code 456. Okay, so you have to follow that. So on IS code 456 on page number 46, table 15 it was mentioned. You can check from there also. Okay. So now we can calculate for the y direction also, that is for second layer of bar. Okay, so it will be 50. Formula will be same, but all you need to do, you have to change the moment. Okay, so it is 193 into 10 to the power 6 divided by 25, and the width will be changed. So it will, so for y direction our width will become as 2500. Okay, and our effective depth is 432 for y direction. So our percentage will come as 0.097 percentage. So here 0.097 is, we can calculate the area also. So it will be 0.097 divided by 100 multiplied with the width multiplied with the effective depth. So it will come as 0.1046, and it is less than AST minimum, that is 0.12 by 100 into 2500 into total depth. So you have to take the total depth for the AST minimum calculation. Always remember that you have to change the gross area only. Okay, so it will come as 1500. So we have to go with AST minimum. You don't use this value. Okay, so here we have to take the number of bar for 1500. Okay, so 1500 divided by pi d square by 4, so it will come as 30 number of bars. Here we are also taking larger number of bar because of the spacing criteria. Okay, so we are taking 16 number of bars. So center spacing for y direction will be calculated by the same method. So our width will be changes, that is 2500 minus 50 from cover from one side, cover from both the sides, till 50 minus 50 minus dia of bar, center of dia bar from both the sides, that is 12 by 2 minus 12 by 2 minus 12 by 2. So and divided by number of bar minus 1. Okay, so it will come as 159 mm. For clear spacing, it will, you have to do 159. So it is 159 divided by minus by minus, you have to do minus center of bar from both the sides, half of the bar, that is 12 by 2 minus 12 by 2. So it will come as 147 mm. So this will be your clear spacing of the bars. Okay, so now it is less than 150 here also, that will be safe as per IS code. So now you have to go for check for one way and two way. So you can calculate only for longer direction, so that if there it is safe, so in shorter direction that will be automatically safe. But here I am going to do for both the directions. Okay, so by interpolation you can find the effective, net upward pressure for both the direction at the critical section, that is at t by a distance uh, d from the face of the column in the periphery. Okay, so you can, because it for a critical section for one way shear in both the direction, that is a distance t from the face of the column, and d is the effective depth of the column. Okay, so first we will find for the x direction, after that we will find for the y direction. So by interpolation you can again use the same method for the calculation of net upward pressure at the critical phase. Okay, in both the directions. So px at critical section is 35.31. You can find it from the same method, that is at 0 it is 62, at 2.5 it is 158. So at 1.909 what is the value of px at critical. Okay, so it is 135.31. So this distance is 2.5 meter, and this will be calculated as 0.591. okay, so how it was defined, this will be half and it will be at the center, that is 430 by 2. okay, so you will come at the center, and after that you have to deduct the this half and plus the effective depth, so you get 0.591. okay, so your BU will be, the nominal shear is, so this will be, shear force will be upward pressure multiplied by area of the critical section. So it will be the average of your both the net upper pressure at critical multiplied by the area of the critical section. okay, so it will be 135.31 plus 158 divided by 2 multiplied by 0.591 into 2, so it will come as 173 kilonewton, and your ultimate shear force will be 1.5 multiplied by 173.34, it will come as 260 kilonewton. Now your nominal shear will be calculated as by the formula tau v is equal to Vu upon V into D. So Vu will be 260 multiplied by 1000 conversion in Newton divided by V into D will be your width, that is 2 meters, that is 2000 mm, multiply the effective depth for x direction, that is 444. It will come as 0.293 Newton per mm square, and your K value will be 1 because your total depth is greater than 300 mm. So as per IS code 456 on page number 72 it is mentioned, so you have to take according to that. So our K value will be more than 300, so we will take the value directly as 1. okay, so percentage steel will be equal to 1470, so this will be the percentage of steel that we have provided for the x direction bars. okay, so it is 1470 multiplied by 100 divided by 2000 multiplied by 444, that will come as 0.165. we will also check in Excel also. okay, yes, this was correct, 0.165%. now tau c dash will be equal to 0.301. how it is calculated, so on in IS code 456 2000 on using table number 19 you have to calculate this. okay, so our percentage still is coming 0.165. okay, so in Excel sheet it is mentioned, you have to just fill the details. So our percentage still is 0.165. okay, and your 0.165% still will lie between 0.15 and 0.25. okay, here if you see, so you have to just put the, okay, 0.15 here we have done, and 0.25 here it is written. Grade of concrete we have chosen M25. So for M25 on table number 19 it is 0.29 for 0.15 and 0.36 for 0.25. So 0.29, 0.36, so your value for the after interpolation for tau c dash will come as 0.301. so that value you have to use here. okay, so it is 0.301. okay, right now for the, so for the design shear you have to multiply it by the value of K. So it will be 0.301 multiplied by 1, so it will come as 0.301, and it is also greater than our nominal share, then only it is safe. So here it will be safe in one way share for the x direction. So I've already mentioned for longer direction if you find it will safe, so for shorter direction if you like to be safe, you don't have, if you don't want to calculate, you don't calculate, that was not a problem. But here we have also done that for the initial design purpose. okay, so py will be calculated by the same method in this direction, so it will come as 126.41 at critical phase. okay, formula will be same. All you have to use the pressure at the y phase only. So upper pressure multiply area of critical section. So half into 126.41 plus 140 multiplied by 0.453 into 2.5. 0.453 multiplied by 2.5. Okay, so your VU will come as 150.85 and your ultimate VU will be 226.28 kilonewton. So nominal shear for y direction will be VU upon B into D. So it will come as VU will be 226.28 multiplied with 1000 divided by B for y direction is 2500 and effective depth for y direction is 432. So it will come as 0.210 and K value is taken as 1 as depth is more than total depth is 500. Percentage still for y direction you have to put this value. So 1809 mm square if steel is provided for y direction, multiply by 100 divided by 2500 into 432. So our percentage steel will come as 0.167. Okay, so now we can use the same table for the interpolation and we will get the value as 0.302 from table 19. So for design distance will be 0.302 multiplied by k, that is 1. So it is 0.302 which is greater than 0.210 nominal shear. So it is also safe here. Okay, see the value, that was too much difference, 0.302 and 0.210. So this will be automatically safe. That's why I'm saying you don't, if you don't want to do for the shorter side, that will be okay. Now we'll go for check for two-way shear. Okay, so this is also called a punching shear. Okay, so where your column does not punch into the footing, so that check is for that value only. And here one more thing, we have to take the effect d value at the average depth. Okay, in this calculation. So your, so we are not taking the whole periphery, we are taking the maximum where maximum upper pressure is coming. So it will come in at this position. Okay, so we are taking for that direction only, so that will be safe for all the areas. And you can also check for y direction. Okay, but here we are using this only. So the average by 2 will be 438 divided by 2, so it will come as 219 mm. We will match in Excel also, and that will be okay. Now your px at critical, that is at d by 2, we have to find. So using the same method on interpolation as we have done earlier, we have to use that method. So our px is for at a critical will be 126.67. So your v will be 127. So we have, you can also use 126.67, it was in points, so I am directly returning 127 plus 158 by 2, that is average of that, multiply by 0.668 plus 2. What is 0.668? This total whole distance. Okay, that is your column length, that was 230 plus d by 2, d average by 2 plus d average by 2, so it will come as 668 mm. Okay, so we have to use this and your total length for the average depth calculation. So it will be 0.668 plus 2 divided by 2 multiplied by this total length 0.816. Okay, so it will come as 154.94 kilonewton per meter square. So U ultimate will be 1.5 multiplied by 154.94, it will come at 232.4 kilonewton per meter square. So your tau v will be VU upon B naught D. And what is B naught? So B naught will be your 668. Okay, so if you are calculating for the whole, you can use as a whole periphery, but we are taking the maximum area, so that will be also safe. Okay, where your maximum upper pressure is coming, so this will also be safe. So VU will be 232.4 multiplied by 1000 divided by B naught is 668, this is a, and 430 is your average effective depth. Okay, so it will come as 0.794 Newton per mm square. So this formula is mentioned on page number 57 on IS code 456/2000. You can check from there also. So now here for tau c dash calculation, okay, the formula will be Ks into tau c, and it is mentioned on page number 58 and 59 on IS code 456. And your Ks will be 0.5 plus beta c. Your beta c will be your ratio of two sides of column, that is 230 by 430, and it will come as 0.53, and your Ks will be 0.5 plus 0.53, so it will come 0.164, but your value for Ks should not be greater than 1, so we are going to take the value as 1 only. Okay, so if it come as less than 1, so you have to take the lesser value. Okay, so tau c dash will be tau c into Ks. Your tau c formula will be 0.25 by fck into Ks, that is 1. So it is 0.25 multiplied by 1 multiplied by square root of 25, it will come as 1.25, which is greater than our tau v, that is nominal tau v that is calculated, that is 0.794. So here it is also passed in two-way check. Okay, now we also go for the check for transfer load at the base. So actual bearing pressure, so we have to find the actual bearing pressure at the base that is coming. So it will be service load divided by area of the column plus moment in x direction divided by section modulus of the column in x direction plus moment in y direction divided by section modulus of column in y direction multiplied by 1.5 for ultimate value. Okay, so P will be 550 into 20 power 6 divided by area of the column will be 430 by 230 plus mx moment in x direction is 100 into 20 power 6 divided by zx of column, that is BD square by 6. So we have taken 6 to upper side, and B will be here 230 multiplied by 430 by 430, and for my it is 50 multiplied 10 to the power 6 multiplied by 6 divided by, so for my it is changes, 430 will be the B and D will be 230 by 230. Okay, so it will come as 32.8 Newton per mm square. So this will be the actual pressure that is transferring at the base, and your capacity or pressure at the base of column which can be distant will be 0.45 into fck. So it will come as 0.4 into 220, it will come as 9 Newton per mm square. So it will come as 0.45 fck, it is 9 Newton, which is greater than, which is less than 32.8 Newton, and it should always be greater than, that's why we have to provide the double bar. Okay, so it is here it is less than, so you have to provide the double bar at the base of the column. Similarly, you can check for the capacity or pressure at the top of the footing, which can be this time. Okay, so it is 0.44 multiplied in bracket A1 by A2, and A1 and by A2 is area of the footing and area of the column. It will come as 22.5 Newton per mm square. Okay, so this value is also less than uh, the load that is transferring actual bearing stress. Okay, through, so you have to also provide the double bar here, like means you have to provide the double bar in both the conditions. Now extra load will be due to pressure at the base of column, it will be 32.8 minus 9, and it is 23.8, and extra load due to pressure at the top will be 32.8 minus 22.5, it is 10.2. Okay, so here extra load will be 23.8, and your extra load due to pressure at top of the footing is 32.8 minus 22.5, it is 10.3, and your extra force will be 23.8 multiplied by the area of the column divided by 1000, so it will come in kilonewton, that is 2354, and at the top of the footing it is 10.3 multiplied by area of the column divided by 1000, it is 1019. So to take the maximum value for the calculation double bar, so extra double bar area will be, so to take the maximum force from here, that is 2354 multiplied 1000 divided by 0.75 Fy. So this formula is used for the calculation of double bar. Okay, so it will come as, so our steel is 500, it will come as 6277 mm square. So if you choose the diameter of bar as 25 mm, number of bar will be calculated as 6244 divided by pi d square by 4, so it will come as 30 number of bar. So you have to provide that our 30 number of double bar. Okay, so final weight of the footing will be, so for the what we have assumed earlier, that is 12% of self weight of the footing. That's why we have taken self weight of footing as 12%. If you take the 10%, then it will come less here after all the calculation. So you have to again increase the self weight of the footing at starting for this match. Okay, so our final weight will be calculated as total area multiplied by the uh, total depth multiplied density of concrete. So our value will come as 62.5 kilonewton. So this will be total weight of our footing, and we have considered 12% of that uh, service load. So it will be 12 by 100 multiplied 550, so it will come as 66 kilonewton. So we have, what we have considered is more than what we got, so that will be safe. Say it will if it will come more than this, okay, so you have to again increase the size self weight of the footing is starting, and again design with the whole system. Okay, that's why we have taken 12%, and we have to, now everything is okay, so we have to provide the bar in this, that is green layer of bar is the bar that is placed parallel to x direction, and the orange layer bar is the bar that is placed parallel to y direction. This blue one is your double bar, and this black top one is your column parts that is coming. Okay, so you have to provide in this shape. Okay, and also you have to also check for the uh, development length. Okay, so that should also be safe. So I've already done the development length lecture. So if you haven't seen that video, I will provide the link at the in the description or end of this video. You can go and check from there only also. So we have covered all the topic in uh, design of eccentric biaxial footing. Okay, so if you like this video, please subscribe to my channel. Thank you.